Okay, and the only thing cut me off there before I could put the units there, so we should have our units there, which is going to be volts. Okay, let's take a look at the next part, and what we have here is we have a different galvanic cell. So they're giving us E. So you missed A and B, or B at least, you can still get C. So what they're asking then is to determine, so based on our E, to calculate our delta G. And so we're going to use our equation where delta G is equal to negative N F E. Okay, and so a couple things there. So delta G is what we're solving for. Okay, and then negative N. This N is going to be how many electrons are transferred. So in this balanced equation here, we're not showing how many electrons are transferred because you donate some and then you use them up and then you take them on again, accept some. So they're not really shown in the equation, but really, if you did it by the half reaction and everything, we're going to be transferring 2 electrons here. So this N is going to have a value of 2 in this situation. F is Faraday's constant, which is going to be 96,500 joules V times mole. So N is going to be moles to cancel this out. And then E is going to be this is going to be the E for the cell, which in this case is going to be the 0.46 that they gave you. Okay, and so when we calculate that, our delta G in joules is going to be negative 89,000 joules. Okay, and so you could do this in kilojoules, would be fine too. Obviously it would just be negative 89 kilojoules, but to get credit on that you need to have the number with the matching units. Okay, and so the next part here is it asks us what's going to happen. So when you have different concentrations, so when we're doing this, we're talking about the Nernst equation. And so we're going to have to think about some equilibrium stuff too, because part of the Nernst equation is going to have to do with Q, which is similar to K. Okay, so in this case, so our Nernst, the energy of the cell, so this is kind of like our actual energy. We can compare that to our standard. So if these concentrations were 1 molar, what it would be, minus a factor, which is going to be RT and F times ln of Q. So that's kind of a complicated factor there, so pay attention to a few things there, but and keep track of units, but everything's, if you take a little time, it should work itself out. So energy of the cell is what we're solving for. Okay, and so we already have our delta E, or our standard E, which was 0.46. And so R in this case, remember we're dealing with energy and joules and stuff like that up here, so R is going to be the 8.3145. And for simplicity here, I'm gonna not include the units because it's hard for me to show them, but keep track of these. And temperature here, so we're talking about at 25 degrees Celsius. So that's going to be 298 Kelvin. We have our N, so N in this case is the same thing we were talking about up there, is how many electrons are transferred. So that's going to be 2. And then F is going to be Faraday's constant, so the 96,500. Okay, times ln of Q. And so Q, again, is like our equilibrium constant. And in this case, what we care about is only going to be the ions, because the only things in solution, solids, remember, that's like a heterogeneous equilibria, not going to be part of it. So our Q is going to equal copper 2 plus, concentration of copper, over concentration of silver squared.